Hello everybody, and welcome to this first video on a series on sophomore functions. Sophomore functions, x to the power of x functions, tetrated functions, etc. They all mean roughly the same thing, and they are all functions of the following form. Okay, so these are sophomore functions. Well, they derive their name from a pair of identities called Sophomore's dream, and these were first proved by Bernoulli. They are as follows. So these are Sophomore's dream. And as I said, these were first proved by Bernoulli in the mid 17th century, I think. So, in this video, we will prove Sophomore's dream. We'll prove Sophomore's dream for the most general case, the following case. Okay, so we'll prove Sophomore's dream for the following case. The integral from 0 to 1 of x to the power of alpha x dx for some real number alpha. Okay, we begin by considering this x to the power of alpha x and investigating its properties with respect to the exponential function. So we begin by considering that we can rewrite this. And then we can rewrite this again as an infinite sum. And now we can take this and substitute it back in up here. And now, thanks to some very useful results in measure theory, leave your answers down in the comments if you know which one it is, but we can swap this integral and this sum. You'll notice that I separated out the alpha n, because alpha, as we've said up here, is a real number, and so this is quite okay to do. Next, we see that we have the sum on the outside, the integral on the inside. And because alpha to the power of n and n factorial are not terms of x, we can take them outside of our sum, outside of our integral, sorry, and we'll get the following. Now then, it's time to make some substitutions. Let's make the following substitution. Let's set u to be the minus natural log of x. The very first thing that we're going to do is change the limits. And now we can substitute back into our integral. So let's see what happens now. We can do some things. First of all, we can use this minus sign to correct our limits. And we can split minus u to the n into minus 1 to the n, u to the n, and factor out the minus 1 to the n. And this will give us something that looks like this. I collected this e to the minus u as well. So, what happens now? We make another substitution. And this time, we're going to set u times n plus 1 to be equal to t. This time, the limits don't change. And again, we rearrange and have the following. And again, we substitute back in to our integral. And again, we can collect like terms and factor out. Now, this should look very familiar to you. This is the gamma function. So, we have, and our n factorials cancel out, and we're left with. Now, we're almost there. But if we take a look back up at the top, these aren't quite the forms that we started with. So what can we do to rectify this? Well, the first thing that we can do is shift our lower limit. If we shift our limit up by 1, then we have to adjust everything inside the sum. Because n plus 1 minus 1 to the power of n plus 1 minus 1 is just n to the power of n. And we can rewrite this further. Now we are ready to make some substitutions. If we substitute in alpha equals 1, in the case of sophomore function 1, then we'll have the following, which is exactly as we have written up at the top. And again, if we set alpha equal to minus 1, then we'll have the following also, which is, as we wrote at the top, exactly the same. So this is a good place to both begin and end. In the next video, we're going to look at this case and we'll explore exactly why this isn't very useful, but this is very useful. Anyway, thank you for watching. I hope you found it useful. Please leave me a comment, feel free to like, and I'll see you in the next one.